Okay, this is chapter 21, video assignment number 1. So, a few things are given to us, but the first step in part A is to find how much did the 1.63 milligrams of lead-206 weigh when it was uranium-238. So it's given to us that uranium-238 decays into lead-206, and a few things are given to us. So basically what we need to find is sorry, I thought the recording had stopped. Basically what we need to find is how many milligrams of lead is equal to milligrams of uranium on the other side of this equation. And it's not going to be like directly 206 to 206, right? So first we convert milligrams to grams, and then grams of lead to moles of lead, and then given the decay equation or reaction, it's a 1-to-1 ratio of lead to uranium, and then 1 mole of uranium is equal to 238 grams of uranium, and then grams to milligrams of uranium. Putting that all together, equating that as 236.6 milligrams of uranium. So that is how much the uranium-238 weighed, or how much the 1.63 milligrams of lead-206 weighed when it was uranium-238. Which makes sense because uranium has a much larger, well, a decently larger molecular weight than lead does. So, part B asks us to find what was the total mass of uranium-238 originally in the rock. So we can take that 236.6 and add it to the 5.51 milligrams that we still have after a certain amount of time that was given to us at the very beginning of the problem. So that's what's left over, and that's what was lost of uranium. So that's 242.11 milligrams of uranium-238. That is the original mass of uranium-238. So then on part C, given the half-life, find the rate constant. So the rate constant equation is ln2, which means half-life, divided by the actual half-life, 4.47 times 10 to the 9th, which we found in the appendix, or in the index M. And that's 1.551 times 10 to the negative 10. So using that on part D, we need to find how old this dang old rock is. So using this equation, -1 over that rate constant that we already found, I didn't want to write it again, so there you go, times ln n sub t over n sub 0. So n sub t is how much we have after that amount of time. This amount of time that we still haven't found yet, which was 5.51 milligrams, divided by, or over, the original mass of uranium, which is 242.11 milligrams, which we found there in part B. And equating that is going to give us 2.4389 times 10 to the 10th years old, which makes sense because the half-life, or in other words, us going from 242.11 milligrams to half of that would be, what was the value that we found? Yeah, 4.47 times 10 to the 9th years. And so this is even more years than that. Like, I don't know how many more years than that is, but times 10 to the 10th. And 5.51 is less than half. So that makes sense. That all checks out. Anyway, that's chapter 21, video assignment 1. Let's go.